All right, let's get right into it. We live in a world surrounded by these incredible engineering marvels, skyscrapers, massive bridges, airplanes, and they're all held together by, well, invisible forces. Today, we're going to talk about how AI is giving us a completely revolutionary way to understand and even master the physics that keep our world from falling apart.
Seriously, have you ever really thought about that? How is it possible to build something so massive that it can actually bend in the wind but never break? The answer is this constant, really delicate dance between two key ideas.
And it really is all about that balance. On one hand, you've got deflection. That's how much something gives away. And on the other, you've got stiffness, which is how much it pushes back. For an engineer, getting this balance right is, well, it's everything. It's the difference between a structure that lasts for centuries and one that fails spectacularly. And for a long time, we had some pretty solid tools to figure it all out.
But things are changing. The old rulebook is being rewritten because the methods that brought us this far are suddenly hitting a wall. They're facing challenges they were just never built for.
For years, the absolute gold standard has been something called the finite element method, or FEM. The easiest way to think about it is like building a super detailed digital twin of a bridge or a wing. Engineers then break that digital model down into millions of tiny little pieces. By calculating the forces on every single one of those pieces, they can simulate exactly how the whole thing will behave. And you know what? It works incredibly well, for the materials we're used to, anyway.
And here's the catch. We're not just building with simple steel and concrete anymore. We're getting into some really wild stuff now. Materials with properties that change from one spot to the next. Laminates inspired by things in nature, advanced composites. The behavior of these materials is just way too complex for our old models, because unlike a solid block of steel, the rules are constantly changing from point to point.
So this is where our new analyst steps onto the scene. When the complexity gets to be just too much for traditional number crunching, AI enters the field.
And look, AI isn't some kind of magic wand that just spits out answers. It's really a powerful pattern-finding machine. It can sift through absolute mountains of data from simulations and real-world tests and start to learn these subtle, complex relationships that our old-school formulas just can't see.
And the whole process really boils down to this. First, you just feed the AI a massive diet of data, tons and tons of it. Then, the algorithm learns. It starts to see that intricate dance between stiffness and deflection in these new, complex materials. And finally, you set it loose to predict outcomes and optimize designs with a speed and an accuracy that honestly was just unimaginable before.
Okay, so that's all the theory. But is it actually working out there in the real world? Well, the results are already pouring in, and yeah, they are pretty darn impressive.
And the proof is right here. This is just a quick snapshot of what's been happening. You've got Zhang in 2024 improving accuracy for predicting the health of structures. You've got Li back in 2021 using it to reduce tiny deformations in manufacturing. It's happening everywhere, from advanced materials to the roads we drive on.
And this quote really nails the key benefit. When you're dealing with these complex composites where every single fiber and angle matters, the AI models are just flat out more accurate than the classic methods. And that's the whole point, right? We're getting a much clearer picture of how things are going to behave before we ever build them.
One of the coolest areas for sure is this bioinspired design. Researchers are looking at nature's own engineering, like bone or wood, which have this incredible graded stiffness that makes them super resilient. By having AI analyze these natural systems, we can actually design new materials that are way better at stopping cracks right in their tracks. It's amazing.
And this is having a huge impact on the factory floor too. Work by Li showed that using AI to guide decisions during the manufacturing process can dramatically reduce those tiny, unwanted deformations in parts. That means less waste, higher quality parts, and just better performance overall.
And this tech isn't just for spaceships and exotic lab materials. It's literally hitting the road. Teams like Simonens are using AI to get a much more sophisticated understanding of pavement stiffness. What does that mean? It means better road design, smarter maintenance schedules, and yeah, a smoother, safer ride for all of us.
So when you kind of step back and look at all of this together, it becomes really clear. We're not just talking about a fancier calculator here. This is a fundamental shift in how we think about engineering itself. We're moving away from the old way of just analyzing a blueprint and, crossing our fingers that it holds up. We're entering a new era of dynamic, intelligent health management, where we can actually monitor a bridge or a building in real time and predict problems before they even happen. So why should you care about any of this? Because it means lighter planes and cars that are way more fuel efficient. It means safer buildings and bridges that can literally tell us when they need a checkup. It means we can innovate and create incredible new materials faster than ever before. It leads to smarter, more resilient solutions to pretty much everything.
So, the final thought I want to leave you with is this. If AI can help us completely rethink the very stuff we build our world with, what comes next? What kind of impossible structures are we going to design? The future is being built as we speak, and it's being built intelligently.